Our universe was built by chaos. The story of everything, including you, begins with a violent act, galaxies crashing together in the dark. By the end of this journey, you will know exactly how these ancient collisions forged the very atoms that make up your body. We will uncover how something as destructive as a galactic merger could possibly create the building blocks of life, and why our own Milky Way is on a fatal collision course with a cosmic neighbor. What do you believe connects your existence to the emptiness of space? From a state of near-perfect uniformity, the infant universe began to develop flaws. That hot, dense soup of particles, expanding at a furious rate, was not entirely smooth. Tiny, random quantum fluctuations, smaller than a single atom, created minute ripples in the fabric of everything. These were the universe's first imperfections, and they were absolutely vital. Gravity seized upon these tiny density differences, these slightly denser patches of the cosmic sea. Over hundreds of millions of years, gravity patiently pulled, drawing matter toward these seeds. What began as a microscopic irregularity grew into a vast cosmic web of dark matter and gas, a scaffolding upon which everything we see would eventually be built. This is the profound truth of our origins, that the largest structures in existence, galaxies spanning hundreds of thousands of light years, owe their existence to the tiniest of beginnings. This foundational era, often called the Cosmic Dawn, was not a gentle awakening but a violent and chaotic birth. It set the initial conditions for a universe destined for collision. Without those primordial quantum seeds, without that delicate imbalance, the cosmos would have remained a featureless, expanding fog. There would have been no galaxies, no stars, and certainly no us. Every great collision that was to come, every galactic merger that forged new elements, was a direct consequence of this first, fragile act of structure. The stage was set, and the players were beginning to take their places. Those first galaxies were nothing like the grand spirals we know today. They were small, fragile things, adrift in a vast and darkening cosmos. For a long time, they grew in isolation, pulling in stray gas to build their first generations of stars. But the universe's initial structure, that cosmic web born from quantum seeds, ensured their solitude was only temporary. Gravity began to orchestrate a slow, patient dance. Across immense voids, galaxies felt the faint, persistent pull of their neighbors. These were not the violent, head-on collisions that would come later. They were gentle, cosmic tugs, a gravitational courtship that unfolded over billions of years. Picture two delicate fireflies, drawn slowly together in the immense darkness of a summer night. This was the nature of the first galactic encounters. As these small galaxies, often called dwarfs, drew closer, their mutual gravity began to work a profound magic. The force did not simply slam the galaxies together. Instead, it pulled and stretched them, drawing out long, streaming bridges of gas and dust. Think of pulling taffy, how it stretches and thins. This cosmic taffy, these streams of primordial gas, were funneled relentlessly toward the galaxy's central hearts. And there, in those newly dense and turbulent cores, something ignited. The compressed gas clouds began to collapse under their own weight, and the first great waves of star formation lit up the darkness. This was the true legacy of these early mergers. They were not destroyers but builders. They acted as cosmic catalysts, transforming isolated, quiet dwarfs into larger, more complex structures. The gentle chaos of these mergers provided the fuel and the spark for stellar birth on a scale the universe had never before witnessed. Each encounter built up the galactic core, fattening the central bulges of what would eventually become majestic spirals and ellipticals. Without these incremental, patient processes, the cosmos would have remained a sparse collection of dim, insignificant islands. Instead, these first dances paved the way for everything that was to follow. setting the stage for the evolution of truly complex cosmic ecosystems. But what happens when this delicate dance escalates into a full-scale cosmic collision? The story of our own galaxy is about to take a dramatic and violent turn. But the true choreographer of this cosmic dance remains invisible. Every galaxy, including our own Milky Way, is embedded within a vast, diffuse sphere of dark matter. This mysterious substance emits no light, reflects no light, and cannot be seen by any telescope we have ever built. Yet it makes up about 85% of the universe's total mass. Its presence is felt only through its immense gravitational pull, a force that acts as the invisible skeleton upon which galaxies are built. When two galaxies are drawn together, it is not their glittering stars that meet first. It is their dark matter halos that begin to interact, their gravitational fields merging and warping long before the visible structures ever touch. Think of it like two crowds of people walking toward each other in a pitch-black room, guided by powerful, unseen magnets. The people themselves, the stars and gas, only follow the paths carved out by these invisible forces. The dark matter halos pass through one another, their particles rarely, if ever, colliding. They simply reshape the gravitational landscape, creating a new, combined well of gravity that then dictates the motion of everything else. Researchers at the European Space Agency describe this as the ultimate form of remote control. The luminous stars and gas clouds are merely passengers on a ride orchestrated by the dark matter's gravitational blueprint. This is why galactic collisions can create such beautiful and symmetrical shapes, like vast rings or elegant tidal tails. The visible matter is being funneled and sculpted along the contours of an invisible template. The final form of the merged galaxy, whether it becomes a featureless elliptical blob or a new grand spiral, is largely determined by the properties of these initial dark matter halos. So while we marvel at the brilliant bursts of star formation and the chaotic rearrangements of stellar neighborhoods, we are merely witnessing the aftermath. The real decision-maker, the silent architect shaping the destiny of galaxies, is the dark matter we cannot see. Its elusive nature is the key to understanding why these collisions unfold as they do, and how they have built the cosmic structures we call home. And as this invisible framework guides the galaxies, the visible universe responds with a spectacular, violent light show. Within these cosmic collisions, the real magic happens in the clouds. As galaxies intertwine, their immense reservoirs of interstellar gas do not simply drift past one another. They slam together. Vast clouds, each light years across, are forced into violent collisions, compressed and heated to extreme temperatures. This cosmic pressure cooker triggers an explosive wave of new star birth, a phenomenon astronomers call a starburst. In a relatively short cosmic time, these events can forge millions, even billions, of new suns. Look at the Antennae Galaxies, a pair currently locked in a spectacular merger. Their long, streaming tails, pulled out by gravitational forces, are dotted with brilliant blue clusters, each one a stellar nursery brighter than any found in our quiet Milky Way. This is creation on an unimaginable scale. But what is the precise mechanism that ignites this stellar firestorm? The answer lies in the intricate dance of gas dynamics. When galaxies merge, their gravitational tides and the powerful shock waves from colliding gas clouds act like a giant cosmic blender. This turbulence funnels enormous amounts of raw material, hydrogen and helium gas, directly into the galaxy's central regions. The gas piles up, becoming incredibly dense. In these overcrowded cores, individual gas clouds are no longer stable. They begin to collapse under their own immense weight. Each collapsing cloud fragments, and within those fragments, the pressure and temperature skyrocket until nuclear fusion ignites. A new star is born. This process repeats itself millions of times over, creating a firework display that can outshine the entire parent galaxy for millions of years. As expert Dr. Lisa Cooley explains, these collisions are the ultimate cosmic catalysts, forcing gas into a frenzy of activity that would never occur in isolation. This vibrant transformation is a powerful reminder that in the cosmos, destruction and creation are two sides of the same coin. The violent chaos of a galactic merger provides the very raw materials, the densely packed gas and dust, from which new solar systems can coalesce. It is within these stellar nurseries, forged in the fires of collision, that the elements essential for planets and for life itself are first seeded. But these brilliant starbursts come at a great cost, and they set the stage for an even more dramatic final act. Our own galactic home is not an island destined for eternal peace. The Milky Way is already on an unstoppable collision course with its largest neighbor, the Andromeda Galaxy. Hurtling towards each other at a breathtaking speed of over 250,000 miles per hour, their mutual gravitational pull has sealed a fate set to unfold in about 4.5 billion years. This is not mere speculation. It is a forecast grounded in precise measurements from the Hubble Space Telescope, which has tracked the motion of Andromeda with enough certainty to confirm the coming impact. The two great spiral galaxies will not simply pass by, they will merge, their structures dissolving and reforming over billions of years into a single, massive elliptical galaxy that astronomers have already nicknamed Milkomeda. What will this cosmic upheaval actually look like from within? The vast distances between stars mean that our solar system is unlikely to witness a direct stellar collision. The stars themselves will be flung into wildly new orbits, like a swarm of bees shaken from two separate hives now mingling into one chaotic cloud. Yet, while the stars may simply pass by each other, the sparse gas and dust that fills the interstellar void will not be so lucky. These colossal clouds will slam together, triggering a final, glorious starburst, a brilliant wave of new suns igniting from the chaos. This future event transforms galactic collisions from ancient history into an ongoing cosmic process. We are living in a universe that is still being built, still being rearranged by these immense gravitational dances. The Milky Way and Andromeda are simply the next partners in a ballet that has been ongoing since the cosmic dawn. This invites a profound reflection. Our planet, our sun, and even our distant descendants will be witnesses to a celestial event of epoch-making proportions, a reminder that we are part of a dynamic and ever-evolving cosmos. These galactic collisions are far too slow for any one person to witness in real time. Their entire narrative unfolds over billions of years, a timescale impossible for the human mind to grasp. So how can we possibly understand the intricate steps of this cosmic dance? The answer lies in a digital universe, a virtual laboratory built inside some of the world's most powerful supercomputers. Here, astrophysicists recreate entire galaxies, programming them with the known laws of physics, gravity, hydrodynamics, and dark matter. They set the initial conditions, and then they press play, watching as eons of cosmic evolution are compressed into a matter of weeks or months. Projects like the Illustris TNG simulation are not simple animations. They are complex mathematical universes. They model the interactions of billions of particles, each representing a parcel of dark matter, a cloud of gas, or even a single star. The equations governing their behavior are solved over and over again, trillions of times, to predict how these components will pull, push, and collide with one another. It is a breathtaking feat of computational power, allowing us to rewind and fast-forward through cosmic history. When an expert like Dr. Volker Springel runs a simulation of two spiral galaxies merging, the computer doesn't just show a pretty collision. It calculates the precise gravitational forces, the shock waves from colliding gas clouds, and the subsequent birth of new stars. The simulation might predict the formation of long, graceful tidal tails, those streamers of stars flung into the void, or it might generate a perfect ring galaxy. Then, astronomers can take these virtual predictions and point their telescopes at the real sky, searching for and often finding these exact features in actual merging galaxies. This powerful feedback loop between digital prediction and real-world observation validates our entire understanding of these events. The chaos of a galactic collision is not random. It is governed by predictable, understandable physics. These supercomputer models reveal the underlying order within the apparent chaos, showing us that the beautiful structures we see are the inevitable result of gravity working on an immense scale. They are our best window into the past and future of galaxies, including our own. By studying these virtual mergers, we can look out at the night sky and identify the ghosts of collisions past, the galactic fossils that tell the story of our own cosmic neighborhood. 60 million light-years away, two spiral galaxies are tearing each other apart. Known as the Antennae Galaxies, their long, arcing streams of stars and gas stretch far out into the darkness, resembling the delicate antennae of some colossal insect. This is not a computer simulation or an artist's impression. It is a real-time snapshot of a collision unfolding over a timescale we can barely comprehend. For over 100 million years, these two star systems have been locked in a gravitational embrace, and the Hubble Space Telescope has given us a front-row seat to the chaos. The initial, graceful dance is long over. The galaxies have already swung past each other, their mutual gravity pulling out those spectacular tails. Now, they are falling back in for a second pass, a final merger that will ultimately erase their spiral identities forever. Within their tangled cores, the violence is transformative. Immense clouds of hydrogen gas, forced together by the collision, have ignited into a firestorm of Starbursts. Hubble's sharp eye reveals thousands of these stellar nurseries, appearing as brilliant blue knots and clusters scattered across the wreckage. Some of these clusters are so young, their light is dominated by massive, hot stars that will burn out in just a few million years. Others are superstar clusters, containing the equivalent of 1 million suns packed into a region just a few dozen light-years across. Potential seeds for future globular clusters that will orbit the merged galaxy for eons. Dr. Bradley Whitmore and his team have used observations like these to map the life cycle of this collision. They have watched as shock waves from the colliding gas compressed vast nebulae, triggering the collapse that leads to new suns. The entire central region is a maelstrom of creation, a stellar factory operating at a ferocious pace that dwarfs anything in our own quiet galactic neighborhood. But this brilliant starburst comes with a dark counterpart. The Chandra X-ray Observatory sees a different side of the antennae, a landscape glowing with the intense heat of death. Its images reveal hundreds of bright X-ray sources, which are likely black holes and neutron stars feasting on material pulled from a companion star. Some of these points are ultra-luminous X-ray sources, objects so bright they may contain intermediate mass black holes, the elusive middle children of black hole evolution. The antennae are not just creating stars, they are forging the exotic remnants that stellar death leaves behind. This living laboratory shows us that a galactic merger is not a single event, but a drawn-out sequence of cosmic evolution. From the initial gravitational perturbation that forms the tidal tails, to the intense compression of gas that triggers the starburst, and finally to the eventual calm as the two galaxies coalesce into a single, new elliptical galaxy. Every stage has its own unique signature. The Antennae Galaxies are a preview of a future that awaits our own Milky Way, a vivid demonstration of the creative destruction that has built the cosmic structures we see today. They are a fossil record of a process that is both ancient and ongoing, a fundamental mechanism of growth and change in our dynamic universe. Yet within this grand spectacle of colliding galaxies, a more intimate drama unfolds around countless stars. The vast emptiness of space means our own sun will almost certainly not collide with another star during the Milky Way's future merger. But safety from a direct impact does not mean stability. The real danger to planetary systems lies not in fire, but in ice. As galaxies intertwine, their gravitational fields become a chaotic maelstrom. A star and its planets, once orbiting in a predictable, steady rhythm, can be violently jostled by a close gravitational encounter with a passing star. This cosmic bump can fundamentally reshape a solar system. A planet like Earth, nestled comfortably in its star's habitable zone where liquid water can exist, could be flung into a new, elliptical orbit. This would turn our world into a place of extreme temperatures, swinging from blistering heat to deep freeze. Alternatively, the gravitational perturbation could be so severe that a planet is ejected entirely, cast out into the blackness of interstellar space as a lone, frozen rogue world. This is not just theoretical. Research from the Harvard-Smithsonian Center for Astrophysics uses complex simulations to model these gravitational disturbances. Their work suggests that while many planetary systems might survive a galactic merger intact, a significant number would have their architectures completely rewritten. The gentle gravitational tides that guide comets from the distant Oort cloud into the inner solar system could be intensified 1,000-fold during a merger, leading to a cataclysmic barrage of impacts. Such an event could sterilize a thriving world, but it also carries a paradoxical seed of creation. These same impacting comets and asteroids are thought to have delivered water and organic molecules to the early Earth. A galactic collision, therefore, could be both an apocalypse for some worlds and a genesis event for others, scattering the essential ingredients for life across new planetary systems. We can look to exoplanets orbiting binary star systems for clues about resilience. Worlds that maintain stable orbits in the complex gravitational dance of two stars demonstrate a remarkable tenacity, suggesting that some planetary systems are capable of weathering immense cosmic turmoil. This perspective forces us to confront the fragility of our own place in the cosmos. Was Earth's history of mass extinctions and sudden evolutionary leaps influenced by a distant, past encounter with another star during a long-forgotten merger? The possibility reminds us that our existence is balanced on a knife's edge, a testament to both the adaptability of life and the profound interconnectedness of all things in our dynamic, and sometimes violent, universe. The most violent transformations occur at the very heart of the collision. As galaxies merge, their central supermassive black holes, each weighing millions or even billions of times more than our Sun, begin a gravitational tango of their own. Initially separated by thousands of light years, these monstrous engines are dragged toward the new galactic core by a process known as dynamical friction. Imagine swinging a thick spoon through a jar of honey, the resistance slowly robbing it of momentum. In space, the black holes plow through the dense sea of stars and dark matter at the galaxy's center, their immense gravity pulling on everything around them, which in turn pulls back, slowing them down. This cosmic friction drains their orbital energy, drawing them inexorably closer. For a long time, they orbit each other as a binary pair, a silent dance in the dark. But their journey is not over. As they spiral inward, they begin to stir the surrounding gas with their powerful gravity. This gas, funneled into the center by the larger galactic merger, forms a seething, hot disk around each black hole. Friction within this whirling disk causes the gas to heat to incredible temperatures and glow brilliantly before it finally crosses the event horizon, feeding the black hole and transforming it into an active galactic nucleus. These engines can become so luminous they outshine every single star in their host galaxy combined. Expert Dr. Priyamvada Natarajan describes this process as the ultimate cosmic feedback, where the collision itself provides the fuel that awakens the sleeping giants. Yet, Even this brilliant display is merely the prelude to the final act. When the black holes close to within a few light years, their gravitational interaction with stars and gas is no longer sufficient to bring them closer. They enter what astronomers call the final parsec problem, seemingly stalling in their cosmic waltz. How do they finally merge? The answer may lie in the chaotic environment itself, where a third black hole or a particularly dense cloud of gas can provide the final nudge. Once they are close enough, their fate is sealed. They begin to lose energy by radiating it away in the form of gravitational waves, ripples in the very fabric of spacetime predicted by Einstein's theory of relativity. These waves are not light or sound, but actual distortions in the geometry of the universe. As the black holes spiral faster and faster, these waves carry away orbital energy, tightening their dance in a final, furious rush. Their last few orbits are a blur, and then they collide. The resulting merger sends a powerful blast of gravitational waves across the cosmos. Observatories like LIGO and Virgo have already detected the waves from smaller, stellar mass black holes, confirming this incredible phenomenon. The merger of supermassive black holes would produce waves of a much lower frequency, a deep bass note in the cosmic symphony, which future space-based observatories hope to hear. This final union marks the completion of the galactic collision, creating a single, even more massive black hole that will sit at the quiet center of the new, merged galaxy for eons to come. This final transformation is one of the most profound results of a galactic collision. The elegant, spinning spirals we know so well can be utterly erased, their structure dissolved into a smooth, round, or oval shape. This is the birth of an elliptical galaxy, a process captured in stunning detail by vast astronomical surveys like the Sloan Digital Sky Survey. When two gas-rich spiral galaxies meet, their beautiful disks are the first casualties. The gravitational chaos of the merger violently stirs up the stars, disrupting their orderly, circular orbits around the galactic center. Instead of circling like cars on a racetrack, the stars are flung into a chaotic, random swarm, buzzing around the new galactic core in every possible direction. This is the fundamental shift that destroys the spiral structure, creating the smooth, featureless appearance of an elliptical. But the stars are only part of the story. The gas, the lifeblood for new stars, meets a dramatic fate. A huge portion of it is rapidly consumed in the intense, merger-induced starburst, lighting up the colliding galaxies in a final, brilliant firestorm of star formation. What gas remains is often blown clean out of the galaxy by powerful winds from supernova explosions and radiation from newborn stars. This process, which astronomers like Dr. Sandra Faber call feedback, effectively shuts down the galaxy's ability to form new stars. The result is what they term a red and dead galaxy. Why red? Because without fresh gas to birth new, hot, blue stars, the stellar population ages uniformly. The galaxy's light becomes dominated by the glow of older, cooler, redder stars. This is why we find so many of these red, dead ellipticals in the crowded environments of galaxy clusters, where collisions were frequent in the ancient past. They are the cosmic fossils of violent mergers that occurred billions of years ago, their spiral arms long since forgotten. Each elliptical galaxy stands as a monument to a colossal encounter, a permanent record of a time when two distinct galaxies became one. This evolutionary path reveals collisions as the ultimate cosmic sculptors, directly responsible for the stunning diversity of galaxy shapes we see when we look deep into the universe. They are the architects that can both build up and tear down, forging entirely new galactic identities from the wreckage of the old. These vast, graceful arcs of light are the ghosts of collisions past. Stretching for hundreds of thousands of light years across the void, tidal tails and streams are the long-lasting signatures of a gravitational encounter, the cosmic equivalent of a footprint left in wet sand. Look at the Tadpole Galaxy, a stunning example captured by the Hubble Space Telescope. Its name comes from the magnificent blue stream of stars that flows out behind it, a tail so long it could span the distance between our Milky Way and Andromeda. This is not some artistic rendering, it is a real structure, a direct result of a smaller galaxy being torn apart and absorbed by a larger one. The physics behind these ethereal shapes is a direct application of gravity's relentless pull. During a close pass, the force of gravity is not uniform. The side of the smaller galaxy closer to the larger one feels a much stronger tug than the far side. This difference in force, what scientists call a tidal force, acts like a cosmic stretching machine. It pulls the galaxy apart, drawing out long streams of stars, gas, and dust that are flung into the darkness. These streams are not random debris. They are precise tracers of the gravitational field itself, mapping the history of the interaction. Researcher Dr. David Martinez Delgado and his team have become cosmic archaeologists, using these faint stellar streams to uncover our own galaxy's violent history. By scanning the skies around the Milky Way, they have discovered numerous faint ribbons of stars, the shredded remains of small dwarf galaxies that our galaxy cannibalized over billions of years. Each stream is a fossilized record of an ancient merger, its shape and the motion of its stars telling a story about the size of the victim galaxy and the angle of its final, fatal approach. Without these ghostly trails, these events would be lost to time, their evidence completely smoothed over by the eons. They reveal that even a seemingly tranquil galaxy like our own has a turbulent and violent past, built from the consumption of countless smaller neighbors. These tidal tales are more than just beautiful accidents. They are the visible threads of the cosmic web, the lasting evidence of a universe perpetually building itself through a cycle of creation and destruction. This stellar alchemy begins in the hearts of the most massive stars born from the collision's chaos. Inside these short-lived giants, a frantic race against time unfolds. For millions of years, they fuse hydrogen into helium, but as their fuel runs low, the core contracts and temperatures soar to staggering heights. This allows new, heavier elements to form, layer by layer, like a cosmic onion. Helium fuses into carbon, carbon into oxygen, and so on, all the way up to iron. But here, the process hits a wall. Fusing iron does not release energy, it consumes it. The star's energy production suddenly halts, and the outward pressure that has supported it against its own immense gravity vanishes. In less than a second, the core collapses catastrophically, then rebounds in a titanic explosion known as a supernova. The blast is so incredibly energetic that it forges elements heavier than iron in a single violent burst, scattering them across space. This is how the iron in your blood, the calcium in your bones, and the silicon in the Earth itself were first created. Yet, supernovae are not the only forges in these collision-driven starbursts. An even more exotic process creates the universe's heaviest and most precious elements. When the cores of those massive stars collapse, they can leave behind ultra-dense neutron stars. In the crowded environment of a merged galaxy, these stellar corpses can be gravitationally drawn together, spiraling in until they collide. A neutron-star merger is an event of almost unimaginable power. As two of these city-sized objects, each more massive than our Sun, smash together, they fling out blobs of neutron-rich material. In this extreme environment, neutrons are rapidly captured by atomic seeds, building up elements like gold, platinum, and uranium in a matter of seconds. Dr. Anna Frebel and other astronomers search for the oldest stars in our galaxy, cosmic fossils that preserve the chemical signature of the universe's first enrichment events. Their work reveals that the earliest stars contained only hydrogen and helium, with virtually none of the heavier elements we find today. The dramatic rise in cosmic chemistry, the proliferation of elements from carbon to gold, correlates directly with epochs of intense star formation, the kind primarily driven by galactic collisions. These violent mergers, therefore, are not just builders of galactic structure. They are the universe's primary elemental factories. Every time you hold a piece of jewelry made of gold, you are holding a tangible relic from a cataclysm that occurred billions of years ago, likely in the heart of a colliding galaxy. This profound connection ties the grandest cosmic events directly to our own biological existence. The very atoms that form our bodies were forged in the lives and deaths of stars that were themselves born from the chaos of galactic collisions. We are, in the most literal sense possible, the children of these ancient crashes. The universe has a biography, and its chapters are written in the light of merging galaxies. We can now read this story, charting the grand timeline of cosmic evolution from its fiery, chaotic youth to its more settled present. The James Webb Space Telescope acts as our ultimate time machine, its deep field observations peering back over 13 billion years to capture the faint glow of the earliest star systems. What it reveals is a universe in constant, violent flux. In those first 2 billion years after the Big Bang, the cosmos was a construction site, teeming with small, irregular proto-galaxies. These building blocks were constantly smashing together, a period of frantic assembly that experts like Dr. Garth Illingworth describe as the universe's most formative era. These frequent, violent mergers funneled gas efficiently, igniting the first great waves of star formation and building up the central bulges of what would become the majestic galaxies we recognize today. This was the epoch of peak activity, a time when the cosmic web was being woven at a breathtaking pace. Then, around 10 billion years ago, the universe began to mature. The rate of major mergers gradually declined. With more space between galaxies as the cosmos expanded, the frantic construction slowed to a more measured pace. This transition had a profound effect on galactic life. The readily available gas reservoirs were either consumed in earlier starbursts or blown away, and the rate of new star formation across the universe began to drop. The most massive galaxies had already been built through a history of cannibalism, growing by consuming their smaller neighbors. We see the evidence of this in the ancient red and dead ellipticals that dominate the cores of dense galaxy clusters, their star-forming days long since ended by past collisions. Our own Milky Way represents a quieter chapter in this saga. It is a product of that more violent past, built from the mergers of countless smaller dwarfs, but now it enjoys a period of relative stability, forming stars at a gentle, steady rate. This chronological view transforms our understanding. The universe is not static. It is a dynamic system with a life cycle of its own, driven by the rhythm of collisions. The calm we see in our local galactic neighborhood is simply a lull in a story that is far from over. So what comes next in this billion-year epic? The forecast for our cosmic future is just as dramatic as its past. Our cosmic environment is not a random scattering of islands. It resembles a colossal, three-dimensional spiderweb, with galaxies strung along luminous filaments that stretch for hundreds of millions of light years, separated by vast, empty voids. This is the cosmic web, the largest structure we know, and galactic collisions are the very force that weaves its intricate patterns. These mergers are not chaotic accidents disrupting an otherwise orderly universe. They are fundamental, constructive processes that define the web's architecture. When we look at supercomputer simulations like the Millennium Run, a virtual universe populated by billions of dark matter particles, we see a clear story unfold. Galaxies are not born in isolation. They form along the invisible filaments of dark matter, flowing along these cosmic highways like water droplets on a spider's silk. Their journeys are guided by gravity, and the destinations are the dense intersections of these filaments, the nodes of the web. It is at these crowded nodes where galaxies are most likely to meet, to merge, and to build up the massive clusters and superclusters that define the web's strongest points. The Great Virgo Cluster, home to thousands of galaxies, is one such node, a metropolitan hub built by countless mergers over billions of years. Cosmologist Dr. Carlos Frenk describes this as the hierarchical model of galaxy formation, a bottom-up process where the universe builds from the small to the large. Tiny protogalaxies merged to form the first dwarf galaxies. Those dwarfs then collided and combined to build spirals like our Milky Way. And even now, those spirals are destined to merge with others, creating the giant ellipticals that dominate cluster centers. Each collision is a step in a grand, hierarchical assembly line, a process that has been continuously structuring the cosmos since its earliest epochs. This model explains why we find the most massive, red and dead galaxies in the densest regions of the cosmic web. They are the products of the most frequent and violent merger histories, having consumed all their available gas and neighbors long ago. In the quieter suburbs, along the thinner filaments and in the voids, we find smaller, quieter galaxies that have experienced a more peaceful existence. Our own Milky Way resides in a relatively quiet filament on the outskirts of the Virgo supercluster, a testament to its moderately violent past. This broader perspective connects the intimate story of a single galactic collision to the fate of the entire observable universe. The beautiful, swirling pinwheel of Andromeda and the faint, ghostly streams of cannibalized dwarfs around our own galaxy are not separate tales. They are individual threads being woven into the same immense cosmic tapestry, a tapestry whose pattern is still emerging from the dark. While the cosmic stage is often dominated by colossal mergers, the true architects of galactic growth work on a much smaller scale. The most common building blocks in our universe are not grand spirals, but faint, diffuse dwarf galaxies. These tiny star systems, containing only a few billion stars compared to our Milky Way's hundreds of billions, are the primary fuel for galactic evolution. Their fate is not to collide in a blaze of glory, but to be quietly, steadily consumed. This process, known as a minor merger, is a gentle assimilation, a far cry from the violent turmoil of two equals meeting. As a large galaxy like our own moves through space, its immense gravitational field acts like a vast net, slowly pulling in these dwarf companions. They do not slam into the disk, causing spectacular starbursts. Instead, they are gradually stretched and torn apart over billions of years, their stars and dark matter seamlessly woven into the larger galaxy's halo. The primary body experiences little disruption, its spiral arms remaining intact. Yet it grows steadily more massive with each acquisition. How do we know this is happening? The evidence is written in the sky around us, in faint, ghostly rivers of stars. Surveys like the Dark Energy Survey, which meticulously maps vast swaths of the cosmos, have revealed these stellar streams with stunning clarity. One of the most famous is the Sagittarius Stream, a great loop of stars encircling the Milky Way. This is the shredded remnant of a dwarf galaxy that our own galaxy is currently digesting. As researcher Dr. Beth Willman explains, these streams are like cosmic breadcrumbs, tracing the orbital path and the gradual disintegration of the smaller galaxy. By studying the motion and composition of these stars, we can effectively rewind time, reconstructing the entire history of the merger, from the first approach to the final dissolution. This reveals a fundamental truth about our home. The Milky Way was not born this large. It has grown to its present majesty by cannibalizing dozens, perhaps even hundreds, of these smaller neighbors over the past 10 billion years. Each minor merger is a quiet transaction, depositing a fresh supply of gas to fuel future star formation, and adding a new population of stars to the galactic halo. This gentle, continuous growth stands in stark contrast to the violent, transformative chaos of a major collision. It is the difference between a steady rain that nourishes the soil and a hurricane that reshapes the coastline. Both are essential forces of change, but one builds patiently while the other rebuilds dramatically. And as we trace these stellar streams back to their origins, we begin to uncover the ultimate source of this cosmic building material, leading us to the faintest and most mysterious galaxies of all. Every element in your body has lived multiple lives before becoming part of you. Galactic collisions serve as the universe's ultimate recycling plants, gathering the scattered ashes of dead stars and forging them into new generations of suns and worlds. This is not a one-time event, but a continuous cyclical process of cosmic renewal. When galaxies merge, the immense forces at work do more than just trigger star birth. They churn the galactic environment, spewing out vast clouds of enriched material. Supernova explosions and powerful stellar winds eject heavy elements like oxygen, carbon, and iron from their stellar nurseries, hurling them back into the interstellar void. This ejected material, now laced with the building blocks of planets and life, mixes with the primordial gas of the colliding galaxies. It becomes the raw feedstock for the next wave of star formation. The mechanisms are both violent and precise. Shock waves from the colliding galaxies compress these polluted clouds of gas and dust, triggering gravitational collapse. Within these new stellar nurseries, the next generation of stars forms, but they are born with a richer chemical inheritance. They contain within them the atomic legacy of stars that died billions of years earlier. We can read this history directly in the light of stars. Astronomers like Dr. Amina Helmi practice stellar archaeology, using the chemical fingerprints of stars to trace their lineage. By analyzing the precise abundances of elements in a star's spectrum, they can determine if it formed from the pristine gas of the early universe or from gas recycled through multiple generations of stars. Stars born from the debris of galactic collisions show a much higher metallicity, a term astronomers use for all elements heavier than hydrogen and helium. This enrichment process is the engine of cosmic evolution. It ensures that with each galactic merger, the potential for forming rocky planets and perhaps life increases. The iron in our blood, the oxygen we breathe, and the calcium in our bones were all created in the heart of a massive star that exploded long ago, and were then scattered and gathered once more during a violent merger. Our solar system is a product of this recycling program, a testament to the fact that the cosmos wastes nothing. It perpetually rearranges its raw materials, ensuring that the story of the galaxies is one of endless transformation, where every ending carries the seed of a new beginning. Beyond the pull of gravity and the flash of starlight, another invisible force is at work in these cosmic crashes. Galactic magnetic fields woven through the space between stars act as a subtle but powerful guide. During a collision, these fields are stretched and compressed, becoming intensely amplified. Radio telescopes like the Very Large Array allow us to see this invisible architecture. They detect the faint radio waves emitted by electrons spiraling along these magnetic field lines, tracing out their structure like iron filings around a magnet. What they reveal is astonishing. In merging galaxies, the once tangled magnetic fields can become highly ordered, forming vast, coherent patterns that stretch across thousands of light years. These magnetic highways can channel the flow of ionized gas, directing it toward the galactic center or confining it within colossal filaments. This guidance system directly influences the collision's creative output. A strong, organized magnetic field can provide support against gravitational collapse, potentially slowing the rate of star formation by preventing gas clouds from condensing. Conversely, it can also concentrate gas into dense, narrow streams, creating the perfect conditions for a future burst of stellar birth. Dr. Sui Ann Mao and her team study these phenomena, comparing magnetic field maps of colliding galaxies with the locations of their stellar nurseries. Their work shows that magnetism is not a passive bystander. It is an active participant in the merger's drama. It adds a layer of control and direction to the chaotic process, shaping how the raw material for new stars is distributed. This means the final outcome of a galactic collision, the very structure of the new galaxy that emerges, depends on a delicate interplay between gravity, gas pressure, and these pervasive magnetic forces. To fully understand the story of a merger, we must learn to read the signatures written in this invisible cosmic ink. A seemingly tranquil galaxy like our own Milky Way is a crime scene, and astronomers are the detectives. The evidence of ancient collisions is not always written in dramatic tidal tales, but hidden deep within a galaxy's stellar DNA. To uncover these cold cases, scientists use a powerful tool called integral field spectroscopy. This instrument does not simply take a picture of a galaxy. It dissects its light pixel by pixel, creating a detailed map of both the chemical composition and the motion of its millions of stars. It reveals the galaxy's hidden kinematics, the precise movements of its stellar population. Pioneers like Dr. Michel Capillari use this data to find the ghosts of mergers past. They might discover a group of stars orbiting in the opposite direction to the rest of the galaxy, a clear sign of a smaller system being swallowed whole, and its stars assimilated into a new, chaotic orbit. Or they might find an embedded disk of ancient stars, a fossilized core of a long-dead dwarf galaxy that now lies at the heart of its cannibal. These substructures are the galactic equivalent of finding a foreign accent in a population, a lingering trace of a different origin. The detective work does not stop with observation. Astronomers then feed this stellar data into sophisticated computer models, simulating billions of years of galactic evolution to see which merger scenario perfectly reproduces the motions and compositions they see today. It is a cosmic replay, running the tape backward to witness the crime. This forensic approach reveals a stunning truth, that nearly every massive galaxy we see bears the scars of a violent past. These mergers were not rare cataclysms but fundamental, recurring events in the life cycle of galaxies. What we perceive as a serene island of stars is actually a dynamic, layered archive, its history written in the silent, swirling dance of its suns. These silent architects, the dark matter halos, are not static structures. When galaxies collide, their invisible skeletons are violently reshaped. The collisionless nature of dark matter means these particles rarely, if ever, strike one another. Instead, the two halos pass through each other like ghosts, their gravitational fields intertwining in a complex dance. But this does not leave them unchanged. The gravitational turmoil can strip dark matter away from the outer regions of a galaxy, flinging it into the intergalactic void. Alternatively, the halos can be stirred and heated, their particles sloshing back and forth before settling into a new, combined configuration that is radically different from the original pair. This redistribution of dark matter fundamentally alters the galaxy's gravitational potential, the invisible landscape that dictates how stars and gas will move for billions of years to come. How can we possibly map something we cannot see? The answer lies in the way gravity bends light itself. Astronomers like Dr. Simona Vegetti use a powerful phenomenon called gravitational lensing. When light from a distant galaxy travels through the universe, the gravitational pull of a foreground galaxy cluster, which is dominated by dark matter, acts as a colossal lens. This lens magnifies, distorts, and sometimes even multiplies the image of the background galaxy. By meticulously analyzing these distorted images, researchers can reverse engineer the distribution of mass in the foreground cluster, effectively creating a map of its dark matter. In merging systems, these maps reveal the dark matter's response to the collision in stunning detail. They show how the invisible halos are offset from the visible starlight, or how they form smooth, diffuse clouds that envelop the entire wreckage of the merging galaxies. This interplay between dark and visible matter is a delicate gravitational partnership. The dark matter provides the overarching framework, the deep gravitational well that holds everything together. The visible stars and gas, in turn, respond to that framework, flowing along its contours and lighting up the regions where the dark matter has funneled them into dense concentrations. A galactic collision is therefore a conversation between the seen and the unseen. The dark matter dictates the overall choreography of the merger, while the luminous matter provides the brilliant, responsive performance we can observe with our telescopes. This understanding reveals that the legacy of a collision is not written only in the rearranged stars or the newborn stellar clusters. The deepest and most lasting imprints are left on the dark fabric of the cosmos itself, an invisible architecture forever altered by the chaos. The chaos of a galactic collision may feel impossibly distant from the quiet miracle of a living cell. Yet these two realities are intimately linked. Every element essential for life, from the carbon in our DNA to the phosphorus in our bones, was forged in the fiery hearts of stars and then scattered across the cosmos by these immense mergers. When galaxies collide, they act as colossal distribution networks, churning their enriched contents and seeding vast regions of space with the raw materials for planets and, potentially, biology. Astrobiologists like Dr. Dimitar Sasilov point to a profound truth, that without these violent events, the universe might remain a sterile expanse, lacking the complex chemical diversity that biochemistry demands. The heavy elements created in supernova and neutron star mergers are blown out into the interstellar medium by the very shock waves and stellar winds that a collision unleashes. This polluted gas, now rich with oxygen, nitrogen, and iron, later cools and condenses to form new stars and their planetary systems. These second or third generation solar systems are born with a rich inheritance, a pre-made toolkit for building rocky worlds and perhaps life itself. But the delivery mechanism extends beyond mere elemental enrichment. Consider the role of comets. The gravitational turmoil of a galactic merger can disrupt the icy reservoirs at the outer edges of solar systems, sending a hail of comets inward. While such a barrage could spell doom for existing life, it could also be a genesis event. These frozen travelers are known to carry water, ice, and complex organic molecules, the very prebiotic materials that could seed a barren world with the ingredients for oceans and the first sparks of life. Our own Earth may have received its water and its amino acids from just such a cosmic delivery, triggered by a gravitational nudge from a passing star during a long-forgotten galactic encounter. This connection transforms our understanding of place. We are not just living in the universe, we are a product of its most violent and creative processes. The calcium in your teeth, the oxygen in your lungs, every atom that defines you, was likely gathered and delivered during a chaotic merger that occurred billions of years before our sun even ignited. Our existence is a testament to a cosmos that builds through collision, a universe that recycles its stardust into something capable of looking back and wondering how it all began. Yet this era of cosmic construction has an expiration date. An unseen force, dark energy, is steadily stretching the fabric of space itself, accelerating the universe's expansion. As this acceleration continues, the cosmic web begins to fray. The vast filaments that once guided galaxies together will stretch and thin, their gravitational pull weakening against the relentless outward push. Cosmologists like Dr. Lawrence Krauss project a future where dark energy becomes the universe's dominant architect. In this lonely cosmos, galaxies beyond our immediate local group will begin to recede, their light reddening and fading as the space between us expands faster than light can traverse it. The great construction sites of the universe will fall silent. The era of large-scale galactic mergers, the very process that built the most massive galaxies, will effectively come to an end. What happens to the galaxies left behind? Our own Milky Way, Andromeda, and their smaller companions are gravitationally bound, an isolated island in an ever-darkening sea. Their fate is already sealed, destined to merge into a single, giant elliptical galaxy, Milkomeda. This will be the last great collision in our cosmic neighborhood, a final act of assembly before the long isolation begins. For trillions of years, this new galaxy will evolve in solitude, its star formation slowly flickering out as its gas reserves are depleted. The brilliant starbursts and the violent awakening of black holes will become memories frozen in deep time. This cosmic endpoint offers a profound shift in perspective. The chaotic, creative period of galactic collisions is not the universe's permanent state, but rather a brilliant, defining phase in its youth. We are living in a special epoch, a golden age of galactic interaction, able to witness the dynamic processes that forge the elements and structures we see today. The universe began in a hot, dense state, matured through an era of violent construction, and is now entering an unimaginably long, quiet adulthood, drifting towards a future of cosmic solitude. The collisions that created us were a fleeting, yet essential, chapter in the eternal saga of the galaxies. Our ability to witness these cosmic crashes is a triumph of human ingenuity. For centuries, galaxies were little more than faint, fuzzy patches in the eyepieces of telescopes. We knew they were there, but their true nature, their motions, and their violent interactions remained a blur. The revolution began when we learned to leave the atmosphere behind. The Hubble Space Telescope, orbiting high above the distorting effects of Earth's air, gave us our first crystal-clear view of the chaos. It was Hubble that captured the Antennae Galaxies in stunning detail, transforming them from faint smudges into a sprawling canvas of stellar birth and destruction. Its sharp eye revealed the delicate tidal tails, the brilliant blue star clusters, and the dark, dusty lanes that told the story of the collision. But Hubble was only the beginning. The James Webb Space Telescope, with its infrared vision, peers through the very dust that obscures these cosmic nurseries. It sees the heat signature of stars forming deep within colliding clouds, revealing the earliest stages of a process that was once completely hidden from our view. These space-based observatories act as our time machines, but they are not working alone. On the ground, a clever technology called adaptive optics fights back against the atmosphere's blur. These systems use lasers to create an artificial guide star in the sky, measuring the atmospheric turbulence thousands of times per second. Then, they deform the telescope's mirror in real time to cancel out the twinkling. The result is an image from Earth that can rival the clarity of Hubble, allowing us to monitor galactic collisions with a precision once thought impossible. Yet, a beautiful picture is only the start. The real magic lies in dissecting the light. Through spectroscopy, we can take the light from a single pixel of a distant galaxy and split it into a rainbow of colors. Dark lines in that rainbow act as a cosmic barcode, revealing the galaxy's composition, its temperature, and even its speed. This is how we know galaxies are moving toward or away from us, and how we measure the intense winds blowing from their starburst regions. As Dr. John Mather, a Nobel laureate for his foundational work on the cosmos, often notes, these technological advances have moved our models from the blackboard to the sky. We are no longer just imagining how galaxies collide, we are collecting the hard data that proves it. This flood of information from Hubble, Webb, and advanced ground-based telescopes is then fed into the supercomputers that run our cosmic simulations. The virtual universe and the observed universe are now in a constant, productive dialogue, each validating and refining the other. Our window into the cosmic construction zone has been flung wide open, and the view is forever changing our place in the story. Our very existence is a testament to cosmic turbulence. This scientific truth that we are built from the debris of ancient galactic crashes carries a philosophical weight that reshapes our self-perception. For much of human history, we saw ourselves as the center of a universe designed for our benefit. Now, we understand that our planet, our sun, and the atoms that form us are the products of violent, random encounters between galaxies. There was no grand design guiding these events, only the relentless, mindless force of gravity acting on a universe seeded with quantum imperfections. This knowledge fundamentally challenges the idea of a preordained destiny, replacing it with a narrative of profound chance. We are here not because the universe intended it, but because a sequence of unlikely collisions unfolded in just the right way over billions of years. The astronomer Carl Sagan captured this elegantly when he said that we are a way for the cosmos to know itself. We are the universe become self-aware, a fleeting moment of consciousness arising from the chaotic dust of its own construction. This perspective does not diminish us, but rather redefines our significance. Our importance lies not in being the pre-planned goal of creation, but in our capacity to observe, to wonder, and to comprehend the magnificent story that produced us. The sheer scale of this reality invites a deep and necessary humility. Our individual lives, our civilizations, and even our entire species occupy a mere blink of cosmic time. We live on a speck of rock orbiting an average star, on the outskirts of a galaxy that is itself just one of billions. The forces that shaped us are so vast and impersonal that our personal struggles and triumphs can feel vanishingly small. Yet, this feeling of insignificance is also liberating. It releases us from the burden of cosmic centrality and connects us to something infinitely larger. The oxygen in your last breath was forged in a star that died in a collision long before our solar system was born. The calcium in your bones was scattered across space by a supernova explosion. You are not just living in the universe, you are a temporary, conscious assemblage of its most ancient and violent history. Every one of us is a living monument to the dynamic, creative, and often destructive forces that have shaped the cosmos for 13 billion years. This connection transforms the scientific narrative into a deeply personal one, inviting us to see our own stories as brief, brilliant chapters in an epic saga of galactic evolution. The hunt for colliding galaxies is no longer confined to professional observatories. Some of the most important discoveries now begin on the home computers of ordinary people, volunteers who lend their eyes and curiosity to science. This global movement, known as citizen science, has fundamentally changed how we map the cosmic dance. Projects like Galaxy Zoo invite anyone with an internet connection to look at real images of galaxies from telescopes like Hubble and the Sloan Digital Sky Survey. Your task is deceptively simple: to classify what you see. Is that galaxy a smooth ellipse, a majestic spiral, or is it something strange, distorted, caught in the act of a cosmic crash? The human brain is remarkably adept at recognizing these subtle signs of interaction: the faint bridges, the warped disks, the delicate shells that automated algorithms can easily miss. It was volunteers, not computers, who first spotted a whole new class of objects: the rare and beautiful green P galaxies, small, compact systems undergoing intense star formation, likely triggered by past mergers. These discoveries, noted by project founder Dr. Chris Lintott, are not just curiosities. They provide crucial data points that help professionals understand the full spectrum of galactic evolution. Every classification made by a volunteer is a piece of a vast puzzle, helping to sift through millions of images to find the most interesting candidates for further study. This collaborative effort democratizes discovery. It proves that you do not need a PhD to contribute to the forefront of cosmology. The story of the galaxies is a human story, one that belongs to all of us. By participating, we become active witnesses to the universe's grand narrative, sharing in the collective wonder of uncovering secrets hidden in the deep field of space. This shared endeavor connects us directly to the cosmos, transforming passive observation into a global partnership for understanding. The story of the cosmos is written in the atoms of your body. Every star you see on a clear night is a reminder of the ancient, violent encounters that forged the very elements of life. We have traveled from the first quantum seeds of structure to the future collision of our own galaxy, witnessing how creation and destruction are forever intertwined in an eternal dance. This grand saga of collisions is not a relic of the distant past. It is the ongoing story of our cosmic home, a narrative of constant renewal written across billions of years. Let this understanding transform your gaze upon the heavens. When you look at the Milky Way's faint band of light, see more than a static picture. See a dynamic river of stars, born from ancient mergers and destined for a future transformation. Each point of light is a chapter in this epic, and we are the conscious result of its most dramatic pages. The universe is not a static museum, but a living, breathing construction site, and we are its most recent, wondrous product. I invite you to share your own sense of wonder in the comments below, to tell us how this story has changed your perspective. If you want to continue this journey of discovery with us, subscribe for more explorations into the deepest mysteries of space. Together, we can keep reading the stories written in the stars, for in understanding the collisions that created us, we truly find our humble and magnificent place in the infinite tapestry of existence.